And using the result from the previous slide, we can also figure out the force between two parallel wires that are separated by a certain distance, just like shown here. Here we have two parallel wires that are separated by the distance d, and then the first wire has a current I1, the second wire has the current Y2, and they are flowing along the same direction. Okay, so what will be the force between them? And we first have to think about why there is a force. So the reason why there is a force is because the one wire will create a magnetic field around it, and that magnetic field will interact with the current of the other wire. Okay, that is why the magnetic force will appear. So we first have to think about what will be the magnetic force given by the first current acting at the location of the second wire, right? So, okay, this figure on the upper part actually gives you such a situation. Here we have a first current I1 flowing along this direction, and by using the right-hand rule, we know that the encircling magnetic field will be going like this. And at this position where the second wire is located, magnetic field will be going up. And what is the size of this magnetic field? According to what we have learned in the previous slide, it has to be given like this. Okay, so here the current has to be the current of the first wire, and then the distance will be the distance between the first wire and then the position where you want to consider. And in this case, this will be the position of the second wire. Okay, and then what will be the force? Now here, okay, in this figure, so okay, we have redrawn the figure so that there will be a magnetic field going up, and then the current will be flowing this direction. Then what will be the magnetic force? We already learned this equation. Okay, so it will be the current multiplied by the length vector cross-producted by the magnetic field vector. And in this case, which current? Here, this current has to be the current of the second wire, which is filling the magnetic field, right? So this will be I2, right? So remember, this will be I2, and this magnetic field is coming from the first wire. So this is the magnetic field we already calculated. Okay, so this is B1, and then L will be the any length of this wire. Okay, so which means that when L is infinitely long, the size of the force will also become infinitely large. So we cannot really calculate the force for the infinitely long wire, but you have to define the length of the wire. So anyway, if you define the length to be L, then L will go in. So this is finally the size of the force between the two. Make sure you understand it contains both I1 and I2, and then the length of the wire, and then we have to divide it by the distance between them. Okay, so here, and then we have to think about the direction too. Okay, so now the current is not a vector, but current gives you the direction of this L vector. So therefore, by making a cross product between L vector and B vector, this will be the direction of the force. So it means the second wire will be pushed closer to the first wire, right? Okay. Then how about the opposite situation? How about the force given by the second wire acting on the first wire? Actually, you can also follow the same logic and think about the magnetic field coming from the second wire, which will be going like this. And at the location of the first wire, the magnetic field will be going down, and then it's going, okay. So, and then you see that now L vector will be going this direction. And what is the size of this magnetic field, B2? It will be, of course, the, if you compare with this, B2 will be mu naught I2 divided by 2 pi d, right? Okay. And then finally, again, using this equation, now in this situation, this current has to be I1, right? So then this, if you insert them, in fact, you get the same side of the force. So force acting by the first wire on the second wire is actually equal to the force acting by the second wire on the first wire. Okay, but then here again, if you make a cross product between L vector and B vector, you see that now direction is actually opposite. It's going that direction. So again, the first wire will be pushed closer to the second wire. And so you can summarize that if two wires are running parallel in current, then they will be pushed closer to each other. Okay, and then in fact, even without calculation, I could have immediately told you that the force acting on the first wire by the second wire is simply minus of the force acting on the second wire by the first wire. Why? I was able to know this without calculation? It is because of the Newton's third law. Newton's third law immediately tells us that when two objects are exchanging force or interacting, the force they give to each other are same in size but opposite in sign. Okay, so even in the case of magnetic force, Newton's law is already satisfied. Okay, and finally, what if the direction of the current, directions of the two currents are not parallel but anti-parallel? Suppose now one current is flowing, say, this direction, and the other current is flowing that direction. Okay, so let's quickly try to think about it. Now the first wire, again, we already said that in this location, the B will be acting in this direction, right? Then if current is flowing that direction, that will be L, right? And then making a cross product between L and B, force will be going that direction, right? So therefore, when the I1 and I2 are flowing along opposite directions, of course, the size of the current will be the same as we have calculated here, but these two wires will be pushed away. So you can finally summarize that two parallel currents will experience attractive force, while two anti-parallel or two currents flowing in opposite directions will experience repulsive force. Okay. The Biot-Savart law is in fact very powerful law from which you can calculate magnetic field for any configuration of current distribution. But sometimes the integration may be very difficult, right? So let me introduce you another law which can be very convenient when you try to calculate magnetic field, and it is the Ampere's law. Okay, this Ampere's law states that the line integral of the magnetic field along any closed loop, which we call Amperian loop, is proportional to the total amount of electric current enclosed by this loop. Okay, this is what it's saying. Can you understand what it is? And we can also use the mathematical formula to show you that this is the Ampere's law. Okay, so what it's saying is given as an example here. So now suppose there are electric currents, many electric currents in fact. So we have 5 electric currents here, only one, I2, is actually going down, right? In this situation, now suppose you set up a closed loop. So example is shown here. Starting from here, you go around, and then you come back to the same position. So this is an example of an Amperian loop. And then suppose you try to integrate the magnetic field going around this. So it's given here. So magnetic field is a vector, and then when you go around the loop, this ds will be the length vector representing a small portion of this loop. So when you integrate this, you have to make a dot product because these two are vectors. And then this symbol of integration with the circle on it, it actually means that you are integrating over a closed loop, right? You have seen this in the case of Gaussian surface. So when you integrate over the closed surface or Gaussian surface, we also had this symbol, right? And so this amount, the result of this integration is proportional to the total amount of enclosed current, and the proportionality constant is this permeability constant. Okay, so in this example shown on the right, now out of the 5 currents, this I4 and I5 are outside of this loop, so you don't have to think about them. But this out of 3 currents, 1, 2, 3, 1, 3 are going up, and the current 2 is going down. So if you suppose the going up is positive, then the calculation has to be done in such a way that amount of enclosed current will be I1 minus I2 plus I3. Okay, and here one thing you have to remember is that how to set up the definition of the direction of the current. Okay, always remember we are using the right-hand rule. So therefore, when you are actually in this example shown here, when you have a Amperian loop going around like this, then use the right-hand rule so that your 4 fingers will be pointing along the direction going around the loop, and then your thumb will be pointing up, right? Then the current going up will have the positive value, while the current going down will have the negative value. Okay, so which means that now if you are going around this loop clockwise, if you are going around this loop clockwise, then you have to flip your hand and your thumb will be pointing down, right? Then if you set up the integration that way, then I2 will have the positive value and I1 will have the negative value. Okay. And then by now you probably have already got some idea that it sounds very similar to what we have learned about the Gauss law for electric field, right? In the case of Gauss law, which is shown here, we integrated the electric field around a closed loop, and then such integration was proportional to the total amount of enclosed charge, and then the proportionality constant was inverse of this permittivity constant. Okay, right? And now here in this case we integrate around a closed surface because the charges can be contained inside the closed surface, right? But in the case of current, since the current has to go around the loop by themselves, you cannot really enclose the current by this closed surface. So that is why in the case of Ampere's law, you have to think about a closed loop instead of closed surface. And now what matters for the magnetic field is of course the current, while the electric field comes from the electric charges, right? So always try to compare between this magnetic field case and electric field case. So, and make sure you understand they look similar, but not exactly similar. There will always be some difference, but the baseline will be that they are very similar. Okay, so there will always be analogies. And just like the case of Gauss law, when we try to use the Gauss law, the calculation was becoming very simple when you had the good symmetry of the charge distribution, right? So Gauss law was very useful when you had a symmetric distribution of the electric charges. And just like that, when you try to use the Ampere's law, think about the symmetry of the current distribution. And if there is a good symmetry, then calculation will become very simple.